This is our first video for Chapter 6. In it, I'll be discussing wave properties of light. So you may or may not have heard of something known as wave-particle duality of matter. So all matter has both wave properties and some particle properties. What I mean by that, when you think of a wave, you think of the curvature, you think of frequency, wavelength, things like that. And particles are just things that we see in our everyday lives. Velocity, position, things like that. And even human beings technically do possess some wave-like properties, but as matter gets larger and larger, the particle aspect of the wave-particle duality overtakes the wave aspect. So by the time you get something as large as the human beings or anything we can see with the naked eye, we effectively can't notice any of the wave properties. But light, when you get it down really small, can exhibit both properties of waves and of particles. So today I'm going to be talking about the wave properties that it exhibits. So first of all, I'm going to define a few terms. So wavelength which is represented by the Greek letter lambda. So if we have, let's say we just have a curvature here. So basically you can pick any point on the wave, usually picking one of the peaks or valleys is a good idea, and however long it takes to get back to that point. So I started at a peak here and it took all the way to there to get back to the next peak. That distance right there is the wavelength. So it's effectively the distance for one unit of your wave, if you want to think about it that way. Right? Another thing I'm going to talk about is the frequency. Frequency is, so I know this looks like a V, but it's actually the Greek letter nu. And basically, frequency tells you how often waves cycle through. So let's say in this amount of time, this goes through 3 peaks, right? So we effectively, so if we start here with the wavelength, that's 1, 2, so we've got about 2.5 waves in that region. Right, one here, and about a half of one again. Now if I do something like this, there are way more peaks, way more wavelengths in this. So in the same amount of space, this second wave has way more wavelengths crammed in. So that means that it has a higher frequency. Right? Now the speed of light in a vacuum, so speed of light equals 3.0 times 10 to the 8th meters per second. And that can be set equal, and that's represented by the variable c. And c can be set equal to the wavelength times the frequency. So what does that tell us? Well, so I'm just trying to refocus this because it seems a little out of focus. Okay, hopefully that helps. Okay. So what does that tell us? Well, that tells us that there is an inverse relationship between wavelength and frequency. What does this mean to have an inverse relationship? Well, c is a constant, right? This number right here, 3.0 times 10 to the 8th. That's never going to change. So if you have two things multiplied by each other, and they're equal to a constant, if one of them goes up, the other one has to go down. Think about it this way. We know 2 times 4 equals 8. Let's say we increase, or let's say we decrease 2 to 1. So now 1, they have to be equal to a constant, right? So 1 times what equals 8? Well, 1 times 8 equals 8. Right? So as you see, when 2 went down, 4 had to go up in order to remain equal to that same constant value. That's an inverse relationship. So wavelength and frequency are inversely related. If one goes up, the other one has to go down. Another very important concept, and this actually is necessary for this number to be exactly what it is in order for our universe to exist the way that it does. That being said, you don't need to understand why the number is what it is. It's something known as Planck's constant. Planck's constant is represented by the variable h, and it equals 6.626 times 10 to the negative 34th joules per second. Or, sorry, joules seconds. Alright, and again, that's a constant. It's never going to change, and it's necessary for our universe. If it was even slightly different, honestly, our universe would not exist in the way that we know it to. And there's a couple of important relationships with Planck's constant. So one, we can say energy equals Planck's constant times the frequency, h nu. And from this relationship here, if we algebraically solve this for frequency, we'd have to divide both sides by v to get frequency by itself. So that means that the frequency is equal to c over, we have to isolate v, so divide both sides by lambda. That was a brain slip right there. So we get c over lambda equals the frequency. So let me show you. So c over lambda equals frequency, right? So we can substitute this in right here. And then we can say E equals h nu, which also equals h times c over lambda. Okay, so again, the E is the energy, and this tells us that energy and frequency are directly related. So it means if one goes up, the other goes up. Since they're directly related, and frequency and wavelength are inversely related, that means that wavelength is inversely related to the energy as well. So energy is directly related to frequency. And another very important relationship with Planck's constant is something called the de Broglie relationship. So at the beginning of this video, I mentioned that there's wave-particle duality of nature. Well, the de Broglie relationship puts a mathematical equation behind that. So what this one is lambda equals h over mv. Now this is v, that's not nu. So lambda, of course, is wavelength. H is Planck's constant. M here is mass. And v is velocity. Well, obviously wavelength is a wave property. Mass and velocity are both particle properties. So this actually is a way to mathematically relate both the wave nature of mass or of matter and the property or the particle nature of matter, and it relates them using Planck's constant.